Yes, so thanks for having me. I've had several people be super surprised that I'm going to talk about light, so I thought I would just quickly explain, because normally I speak about sound. Okay, so I did my PhD with John Page in Winnipeg in Canada, and I used sound to look at strong scattering and, in particular, Anderson localization. But then I did a postdoc in Paris with Alexandre Aubry, and we did more imaging stuff. What? There used to be labels, so it's like they're a little bit to the side. My geography is not so good. Europe. And what was I saying? Yes, but I had the opportunity to do some experiments with light, which was very challenging for me. And now I work in New Zealand, at the University of Auckland. So I've mostly come back to acoustics. But in the few years that I've been in Auckland, Alex and I have still been looking at some data that I took in my postdoc with him, because we did not understand our results for quite a while. So I'm going to talk about that today. So this is a collaboration with Georg Maret from the University of Constance. Right, so I just wanted to start by, does anyone here not know what this machine is? Maybe some young students? No? Everybody's seen one? Okay, great. So, so this is a overhead projector. So you have this light that comes down, it shines onto this sort of transparent, thin plastic piece, and then what you write on the plastic, it gets projected up here. So now these aren't used anymore. So I think in departments everywhere, there's like stacks of unused transparencies, these thin plastic sheets. This is really nice because you can do a fun experiment with them. So if you take a stack of a bunch of these transparencies and you shine a laser through it, like a little laser like this. It's kind of an interesting experiment because these transparencies probably don't have a lot of quality control about thickness, so they're essentially not random but quite disordered. What am I doing? And the spaces between them, if you're just stacking them, are going to vary over several wavelengths. Whoop. No? Okay. And the approximate size or the thickness of each transparency is going to be on the order of a wavelength. So this means they are going to have fairly strong scattering, which is cool. And then I'm also going to say that absorption is pretty negligible because they're clear. So you could consider this, as a physicist, as a waveguide with sort of random variations in a refractive index. So as you meet each transparency, you have some probability of going through or getting reflected. And then you can measure some sort of transmitted intensity at the other side. So the question is, for you guys, how do you think transmitted intensity will depend on the number of plastic sheets? Anyone want to guess? No? Oh, too soon. Okay, so if you use naive ray theory, then you would guess maybe 1 over n. This is pretty easy to calculate because you just take 2 transparencies and then you just sort of figure out what you get in terms of total reflection, total transmission. And then you can extrapolate this to n transparencies. And you just have to do some sort of geometric series. But as you say, this is ignoring the sort of wave part of this wave, which is that it also has a phase, which will change at each interface. And so if you take a more wave approach to this calculation, which also isn't super difficult, you can see that actually the transmission decays exponentially. And so this is because you have paths which are the same distance. So A and B have taken the same distance, but B will have an extra phase shift because of this interface here. And so this means that you get some destructive interference between these paths, and then you'll have more and more of these as you add more and more interfaces. And so if you actually do the experiment, you will find, hopefully, that you get what's predicted by the wave approach and not is what predicted by ray theory. Okay, so the whole point of this, So this is a really simple example of Anderson localization. The whole point is to emphasize that you have this sort of decrease, an eventual stopping of transmission caused by disorder, and more accurately caused by interferences which are caused by disorder. Okay, so since I'm talking about Anderson localization, I have to put this picture of Anderson, right, that everybody does, and also a picture of his initial paper. So he predicted this in 1958 for quantum charge diffusion. I'm going to talk about classical waves. So normally I'm talking about acoustic waves, so I put the scalar wave equation. But the point of this is that the disorder that we need for localization is going to come in from these deviations in the uniform medium. So deviations in the refractive index or density, as you wish. So our simple example was this sort of 1D calculation. I'm going to talk more about scattering, so waves interacting with small circular scatterers. So for a sort of general idea of how transport is affected by localization, we can contrast it with conventional diffusion. So you have your in conventional diffusion, you have this diffusion equation. So your average wave energy is going to obey this equation. And so you get waves that are sort of spread out from the source, and you can calculate how they should spread, or how their sort of average spatial extent should scale with time, like this, right? And so in this picture, interferences between different wave paths are not important. And then you can have strong scattering, in which interferences start to become important. And so I've sort of drawn it as loops here, but people don't really like this. It's just sort of an easy way to think about how waves might interfere, just like they interfered when we had all our transparencies. And so for strong scattering, you want the particle size sort of on the order of a wavelength, some kind of small mean-free path. And when you have strong scattering like this, you have a high return probability. So this can be thought of as the probability for one of these little walkers to return to a spot that it has previously been. Okay? So if this probability is high, then, yeah, in this picture, interferences are important. And so with an increase in return probability, you'll naturally have a decrease in diffusion, right? Because if you're spending longer in the sample, then it's taking longer to get through the sample. And so this implies that we should renormalize our diffusion coefficient and make it smaller. But then if diffusion is smaller, then you're spending longer in the sample, so then return probability increases even more, and so you get this kind of like feedback loop. So with more and more of these events occurring, the waves are taking longer on average to spread out, and then eventually, if this happens, if this keeps on going and nothing stops it, then you can get localization. So then you have your average spatial extent of your wave energy is limited to a certain spot, or a certain extent, which we call the localization length. And then in 3D, there's this exciting phase transition between these two regimes, which we've seen in a couple of other talks already, or one other talk. So then we say that in 1D and 2D, you can generally always get localization just by making your sample big enough. So we saw that with the transparencies, if you put enough transparencies, eventually you would just have a mirror and you would have no transmission. In 3 dimensions, as we've seen, localization is much trickier to happen, or to get, and it only really happens for when you have a lot of disorder and a lot of strong scattering and some other conditions. So we're going to look for localization in 3D for classical waves. So experimentally, this is pretty tricky. Successes have been had with electrons and cold atoms. And then for classical waves, a lot of success has been had with acoustic waves. But as we've already seen so far, there have not been any sort of definitive success with light in 3 dimensions. And this is still sort of under debate. So experiments with light have generally been examining these sort of white paint powders. We do this because you can get quite strong scattering, and the powder particles can be considered random because they sort of are just packed together. Okay, so previous experiments. So the first sort of exciting experiment with these white paint powders looked at the transmission of light as a function of sample thickness, okay? And so you can calculate what you should get for diffusion and for localization. And so they saw that by changing the particle diameter, so essentially changing the scattering strength, they could get to a point where it looked like they saw localization instead of diffusion. But the problem with this, as we've seen, is that you have absorption coming in which has the same sort of exponential decay. And so it's kind of tricky to decide whether you have localization or absorption. So later on, it was found that this was absorption and not localization. So then, after this, there was quite a nice series of experiments looking at transmission as a function of time. And so again, you can calculate what you should get in diffusion and localization. And again, you can see that you get, at some frequencies of light, you can get diffusion, and some frequencies you get this departure from diffusion, which was exciting because it looked like localization. And, dang it. Oh, whoop. Okay, well, again, you have absorption coming in this exponential way. But worse for these experiments is that you also have fluorescence coming in also in an exponential way. And so all these effects are either masking or maybe mimicking localization. So all these experiments showed that light is really extremely strongly scattered in these media, but they're really hampered by all of these extra effects. So we did a project where we wanted to essentially just look at how light is transporting through these kind of paint powders. And we wanted to do an experiment in which absorption and fluorescence were not important. So we took, so this is a collaboration with Georg Marat because we got the samples from their group and a lot of help to understand the paint powders. So we took basically 3 different kinds of powders. So the names aren't really important. What's important is that they're all very strongly scattering. So previous measurements have estimated this KL, so the wave vector times mean free path, to be on the order of 1. And for 2 of the samples, they are also quite strongly fluorescing. So we compressed them into these little pastilles. The idea behind this was to get even stronger scattering, so they're close packed. For those who are interested, here are some other numbers. So this is sort of the average scatter size, and the transport mean free path has been estimated to be around this. And then you have absorption time, which is on the order of a nanosecond. So we looked at these paint powders using a type of low coherence interferometry. Okay, so the basic setup is here. So this is a setup that was in the lab before the basic setup was in the lab before I got there, done by Amaury Badon. So the basic idea is that you have this little Michelson interferometer here. So the source is a white light, essentially a halogen lamp. It shines onto this scattering sample, and then the backscattered light is collected by this microscope objective and goes into the 2 arms of the interferometer. Okay, and then everything is collected back at the camera, which is conjugated with the focal plane of the microscope. So what the camera actually measures is the autocorrelation of the scattered wave field. Okay, so here we have, for instance, the autocorrelation of the scattered wave field at this point, or this point on the sample surface, and then a different point on the sample surface. Then you can move one of these mirrors up and down to scan the temporal domain, essentially. So now we have the time-dependent autocorrelation of this wave field. And we can also measure we can also use 4-phase interferometry to measure this is a complex field. The other mirror tilts, so this lets us scan the spatial domain. And so now, if this mirror is tilted, what we see is just the correlation of the scattered wave field, and we're essentially sort of correlating 2 different points on the sample surface here. So this is kind of a special measurement, and the reason it's special is due to this incoherent source. So the idea behind this experiment is based on a rather old idea, initially developed in seismology. So here's the sort of basic picture. You have all this is sort of scattering sample, and then you have an incoherent source, which emits a field into it everywhere. So if you put your detector at point B, and you put another detector at point A, and then you just record basically the noise that's happening, And then you, and then you correlate this noise like this. This correlation should tend towards the Green's function between points A and B, which is pretty cool. So if this seems mysterious to you, I suggest that you check out some of these papers. This can be derived in several different ways. I'm not going to go into it much here, but this has been shown in seismology and then acoustics. And so this optical setup was the first to apply this to optics. So for our optical setup, this T here is integration time of our camera. So if we could have an infinite integration time, then we could extract exactly this Green's function. But we can't have an infinite integration time of the camera. And so what we get looks like this. So here, I don't know why these numbers are not appearing, but it doesn't matter. This is integration time of the camera. And here we see the intensity. So this is just the intensity of this correlation function here. So what's cool about this is that this is something that should essentially evolve as 1 over t. So here we have essentially noise, but then eventually as we increase the integration time, this is going to tend towards the Green's function. And so this should eventually plateau over here somewhere into the Green's function. So even though we can't measure all the way over here, we can essentially fit each of these curves with this expression and then extract this intensity from the noise. So this is a really sort of clean way of estimating this intensity Green's function. Yeah, voila. So, all right. So, essentially, this lets us measure this Green's function between points RA and RB. And it's not actually the Green's function, although I'm going to keep on calling it that. It's really just a response function between these finite size points RA and RB on the sample. And so we can measure this for all points RA, RB everywhere on the sample surface. And you can think of this. So here's an example of sort of the field that we measure. So this is amplitude as a function of time. You can see all these little oscillations. So this is like a multiply scattered signal. You can think of this as including all the different possible paths between points RA and RB. So not just this one, but all the different ones arriving at all these different times, right? So it's really nice to have this Green's function. It's pretty cool. But if I want to look at average transport, what we really want is intensity, right? So classically, we want this ensemble averaged intensity Green's function. So to get this from our experimental, and so this could be considered, because we're essentially multiplying the Green's function by its complex conjugate, now we're looking at all possible pairs of paths inside the sample. And so this gives something like this. So here we have intensity as a function of delta R. So this is the distance between RA and RB, and time. Okay, and so we see that at the origin, so at delta R equals 0 and at time equals 0, we've got sort of a small point, and then from there, the wave energy spreads out as you'd expect. And so here's technically how we calculate this from our experimental measurements. All right, so the takeaway from this, whoops, there we go. All right, so the takeaway from this is that using this kind of measurement, we can have quite a nice, clean extraction of the intensity as a function of space and as a function of time. So this lets us sort of directly examine the spatial temporal spread of the average wave energy inside the sample. What's really nice about this is that we have quite a long range of times. So we can look even at short times here. If you were using a laser and you were trying to look at, say, the transmitted intensity through a sample, then it's quite hard to look at the very early times, mainly because you have to wait for the light to come through the sample, but also because you're using a laser, and so you're really you might have a large signal right at the beginning. So we don't have this, and we actually can go to quite long times because of the way that we extract this intensity from the experimental data, as I showed earlier. And then spontaneous signals such as fluorescence are not included in this measurement at all. And absorption is also negligible in the timescale studied, although we do more to get rid of absorption later. Okay, so we've got this experimental data. Now we want to fit it with some theory. So to do this, as we saw in the talk earlier, yesterday actually, we to have a theoretical description of this intensity, we want to essentially have average over all contributions from all possible pairs of paths between the points separated by delta r. So a lot of these paths are what we would call incoherent paths, which means that they don't have any particular, they're independent from each other. And so these are the paths that give what's called the diffuse halo. So essentially, these are all the paths that are considered in the diffusion approximation. But we also have other paths. Since we're looking at reflection, we've seen these paths before. This gives the coherent backscattering peaks. These are pairs of paths which take almost the same route through the sample, but in different directions. And so you get this overall constructive coherence in the backscattering direction. And then a special case of this is when you have the input and output at the same spot. So this is also could be considered coherent backscattering, but it's a special case which we call recurrent scattering. We'll talk more about this later. So if we take all these possible pairs of paths, you can calculate a prediction for what this intensity should be as a function of space, delta r, and then also time, t. Okay, so this is not super new, and it has already been proven by several different groups over the years. So if you want to see how this exactly comes about, please refer to some of these papers. So essentially, this Gaussian here comes from the diffuse halo, so these incoherent contributions. And then you have this extra part, which is the extra coherent peak from the coherent backscattering. So since we're looking at the sample surface, so not in the far field, coherent backscattering doesn't depend on time. So actually, in this kind of measurement, it's not super interesting to us. But we need it in here so that we can fit our data with our theoretical predictions. So here we see the experimental data again, but it's in a sort of different way. We see sort of slices in time. And here we've normalized the backscatter intensity just by itself at delta r equals 0. So you can see all these are normalized to 1. Okay? So this is, so the red is the theory. So that's this entire thing. And then the little black dashed line is just this Gaussian part. Okay? So you can see that actually the coherent backscattering peak isn't really contributing a lot. It's just a little extra peak on top of this black dashed line. All right, so this fits all of our data really nicely at all of the times. So we have many more times, I just don't show them here. And to characterize the wave transport, we're going to be interested in this term here. It's evolving in space and time. So what we can do is look at how the width of this Gaussian evolves as a function of time, okay? And so this is really nice because it's actually an absorption independent quantity. Because we take this ratio of intensities, any sort of absorption factor which contributes exponentially is going to cancel in this ratio. So if we look at this width squared as a function of time, we get things that look like this. So this is for each different white paint powder. And then if we were in the diffuse, if we were in the diffuse regime, then this, we know, should be linear with time, okay? And this is a measurement that we've done a lot in acoustics. So we know that this works really well. In the diffuse regime, these should just scale linearly with time. And from this, you can actually calculate the Boltzmann diffusion coefficient from the someone help me. Huh? Slope, thank you. Okay, great. Just checking you're paying attention. Okay, so if we try to do this, it doesn't really work. Maybe it kind of fits at long times, but we would really expect these also to go through 0. So, okay, we don't have pure diffusion, so then maybe this is exciting because if we're looking for localization, what we're looking for is departures from conventional diffusion. So if we were in the localization regime, whoa. Yes, okay, if we were in the localization regime, I think this is what I want. Yes. Then, as we saw here, we'd expect the return probability to increase, diffusion to decrease, and then we have this sort of feedback loop. And you can calculate that this diffusion coefficient should be rescaled. So it starts out like this. It depends on several different length scales, including the correlation length, system size, and absorption length. And then since we're looking in reflection, we can define a sort of effective system size. This is essentially the part of the system that the waves see as the wave energy sees as it spreads out. So if we combine these two equations, we can get a time-dependent diffusion coefficient. And we'll note that this is for sample size which is much smaller than the correlation length, so we're not in localization regime, and also for negligible absorption. So this isn't for the localization regime, but this is sort of what we'd expect if we had a significant decrease in diffusion due to a strong scattering. Oh, yes. Okay, so in this case, we should expect that W squared goes as this sort of power of T. So here we've just taken the time-dependent diffusion. Here we've just taken this guy, this time-dependent diffusion coefficient, and substituted in here. And so we get this new function for W squared. So this is going to do something like this. I've just kind of drawn this in here, but we know that essentially in the sort of subdiffuse or localization regime, we should get not a linear dependence on time, but something that sort of slowly bends over, and then eventually, if it's localized, this should plateau at some sort of long time. So this doesn't seem to fit our data either. And at this point, we were we didn't really understand this because it doesn't seem diffuse or subdiffuse or localized. So to get a little bit more clarity, we looked at a different quantity. So that's this recurrent scattering part over here. So essentially, this is just the intensity at delta R equals 0, okay? So if we look at this, we can also make predictions for how this should behave in each of these regimes. So here we have our results from all three samples. They look quite similar. And I'll note that this is just normalized by the intensity at the origin, basically. So in the diffuse regime, we should get this kind of power law. So that doesn't really seem to fit our data very well. And then for subdiffusion or localization, you can do the same kind of calculations that we just did. And you get something like this. So neither of these seem to fit the data either. And then this confused us for quite a while. And something that helped to interpret these results is this quite old idea that localization is prevented by these dipole-dipole interactions between close-packed scatterers. So we already discussed this yesterday in Robin's talk. And as I understand it, the basic idea is this. So you have this Green's function for an electromagnetic wave in some effective medium. And this can be separated into two different parts. The transverse parts is the propagating part, and then a longitudinal part, which takes into account these Coulomb interactions between induced charges from the propagating wave. So these parts are non-radiative dipole-dipole interactions. So normally we don't take this into account because it's negligible if you have a mean free path which is larger than the wavelength. But if you do take this into account, and you calculate your intensity and some other things, then it turns out that, well, essentially you have these things which are going to interfere or give interference terms, right? Because you're calculating this Green's function's intensity. And so Bart van Tiggelen and Sergei Skipetrov have done this. So this is this paper in 2021 that we weren't really sure what they were doing. And so essentially they do some extended independent scattering approximation for radiative transfer. They find that one of these interference terms gives a sort of additional diffuse transport channel. So essentially, when they tried to calculate this more specifically with self-consistent theory, they find that there's a minimum non-zero conductance for any kind of, if you have any kind of contribution from this guy. So I actually just saw Bart give a talk on this a couple of weeks ago, and he doesn't seem to think that there's any kind of open question about localization of light in 3D. And so this is the result that they've gotten. Kind of tricky to prove experimentally because you have to prove that something's not possible. But something that we can compare our results to is another picture of kind of the same idea from this 2016 paper. And so here, they're essentially saying the same thing, but they have a much simpler model, essentially trying to treat scattering and this near-field coupling as competing effects. So the idea here is that, okay, you have some scattering with these like loop paths, essentially waves spending longer in the sample and your diffusion becoming renormalized. But the idea is that if you have any kind of coupling between scatterers which are near to each other, then this can be seen as a kind of energy leak away from these paths. And so eventually, you can have enough of this energy leak such that you don't have enough of these loop paths to give you enough interferences to achieve localization. So in their model, they make this sort of really simple prediction for how this might be seen in an experiment, which is nice. And so essentially, they say that if you think about this as being sort of a competition between the transport cross-section, so for scattering, and a cross-section for this near-field effect, then you can predict some sort of transition time where enough time has passed for this near-field effect to be dominant. So what does this mean? It means that before this transition time, okay, you have a continuous rescaling of D, you have these little loops setting up for a subdiffusion, but then at the transition time you have enough energy leakage to stop this rescaling, and then after the transition time, they predict that you would have conventional diffusion come back again. And so you have some sort of subdiffusion-diffusion crossover. So we can compare this to our results, and it seems to make a lot more sense. So actually, if you just plot the, if you just compare the first early times with subdiffusive behavior, and then you compare the late times with diffusive behavior for all three samples, it fits quite nicely. And so this means that at this sort of crossover, this should be this crossover time that we've calculated here. So you can estimate this sort of crossover time for all three samples. And then what's really nice about our data is that you can go back and try to examine this nicely, or much without absorption, and more directly using this W squared. So we've estimated these crossover times from the previous graph. And we think that so before, after this crossover time, you should have conventional diffusion resume. And so you can fit our data after this crossover times with this linear fit, which looks quite nice. And satisfyingly, we get a diffusion coefficient which agrees with some previous measurements done by Georg's group for all three samples. Okay, and then so before this time, this is where we should have the continuous rescaling of D, so subdiffusion. And this agrees quite nicely with our previous prediction for this subdiffusive regime. So then I'll note that this doesn't quite go down to 0. And we think that that's because we have a ballistic or quasi-ballistic transport. In fact, this is the only way that you could sort of explain how this rapid energy growth at this early times. But this data point is the first one that we can measure. So we think that's what's happening at these early times. Okay, so just to recap exactly what we've done. We've made these first measurements on light, which are totally independent of absorption and fluorescence, on the most strongly scattering samples that we could find. And essentially, to explain our data, we need to sort of consider two regimes. So it looks like at some sort of early times, we have subdiffusion, which agrees with these predictions from self-consistent theory. And then at later times, we seem to have a recovery back to conventional diffusion. And so this picture agrees with the predictions from this 2016 paper by Naragi and Dagariu. So this is good evidence for this renormalization of diffusion being destroyed by these near-field effects. And something that's interesting is that we can calculate the ratio between this cross-section of near-field effects and the transport cross-section. And it's really tiny. So this shows that the near-field effect itself is very small, but it has an effect after many different interactions, so these really long paths. eventually are leading to a significant effect by this dipole-dipole interactions. Okay, so we have some remaining interesting questions, like what is happening at these very early times? So we think that these can be explained by this ballistic or quasi-ballistic transport, but actually in this paper here, they predict that there should be some earlier diffuse regime, which we don't see. But I mean, maybe it's possible that something is happening in these like tiny little time range here. We couldn't really measure that with these particular measurements. And then another interesting question, I think, is how close might we have gotten to localization? So if we have subdiffusion and a sort of renormalization of diffusion, then maybe we were almost at the mobility edge, and then before this was destroyed, or maybe we weren't close at all. And but if we were almost there, then this sort of implies that there's hope for other groups which have proposed doing things to increase the scattering strength, like using resonance scatterers, or like maybe putting some order, some positional order. So I guess to answer this, we would need to compare to some kind of theory which could predict a correlation length or a localization length. And it doesn't really agree with the predictions from Bart and Sergey about, because they would say that we'll never get into localization. So I guess this remains kind of an open question. And then I guess a similar question is, what if we had samples that weren't close packed? So we actually we compressed our samples into these little pills because we thought that would increase the scattering strength, and it probably did. But it probably made this near field interactions worse, right? Because then we have all these particles super close together. So I don't know. Maybe I guess we could talk about whether this would happen if you had particles that weren't nearly so close packed. Yeah, so I think I'll stop there and give me some questions.